Good morning everyone. As you can see on the screen, our talk is about the Booth's multiplication algorithm. These are our group members. Cited here are the topics that we will be covering in later part. So let us start with the introduction to Booth's multiplication algorithm. The algorithm was developed by Andrew Donald Booth in 1950 and is commonly used in computer arithmetic. Basically, Booth's multiplication algorithm is a technique used to multiply two signed binary numbers using shifts and additions. Signed binary numbers are a way of representing both positive and negative numbers using binary digits, that is 0 and 1. In Booth's multiplication algorithm, right shifts are used. This algorithm is more efficient than traditional algorithms, especially for large binary numbers. Coming to the algorithm, the most important part is getting to know when to perform shift operation and when to perform addition operation. Simplifying it, while solving an example, if you come across 0, 1, then first addition followed by right shift should be performed. Similarly, if 1, 0 is found, then subtraction followed by right shift is performed. In case of 0, 0 and 1, 1, only right shift is performed. So,
Let's observe the flowchart for Booth's algorithm. We start by initializing the accumulator to 0, the flip-flop q-1 to 0 and storing the multiplicand in a register. Then we store the multiplier in another register and store the count, that is number of bits in the multiplier, in another register. Next we check the bits q0 and q-1. If they both are 0 or both 1, we perform an arithmetic right shift on the accumulator q and q-1 and decrease the value of the count by 1. If q0 and q-1 are 0 and 1, that indicates the end of the sequence, and we store the sum of the accumulator and the multiplicand in the accumulator. If q0 and q-1 are 1 and 0, which indicates the beginning of a sequence of ones, we store the result of subtracting the multiplicand from the accumulator in the accumulator. After performing the operation, we perform an arithmetic right shift on the accumulator q and q-1. We repeat this process until the count becomes 0, which means we have traversed all the bits of the multiplier. Once the count becomes 0, we stop the process and the result is available in the accumulator. This is how the concept of Booth's algorithm is implemented.
So here is an example to explain the algorithm. The first example is the multiplication of two positive numbers, that are 11 and 4. We have considered 11 as the multiplicand and 4 as the multiplier. In the bracket next to them, we have written the numbers in their binary form. We have also written the value of -m, which we would use during the calculations. The number of bits in these numbers are 4. Therefore, we would need 4 iterations or 4 passes to complete the calculation. Starting with the calculation, all bits of the accumulator are always 0. The value 4, which is the multiplier, is written in the binary format under the q column, and the value of q-1 always starts with 0. So in the first pass, we will compare the last bit of the q column and the only digit of the q-1 column. If both of the digits are 0, then we will shift all the bits to the right. So the way you do this is you shift all the individual bits to the right. The last bit of the q column gets written as the first bit in the a column as well as in the q-1 column. The bit in the q-1 column gets overwritten and is not copied anywhere. So in the first iteration, the last bit of the q column and the only digit of the q-1 column are 0 and 0. So we have directly shifted all the bits to the right. The obtained answer is copied in the second iteration. Comparing the two values, they are 0 and 0 again. So a direct right shift is done. When you come to the next iteration, we can see that the two bits are 1 and 0. Therefore, we have done a a-1 operation where we have added the value of the accumulator and -1, which we have calculated previously. You can see the calculations on the right. The value that we have obtained is copied into the accumulator and the rest of the columns are written as it is. After we are done with the calculation, we will move all the elements to the right. In the last iteration, which is the n-1 iteration, you can see that the last digit of the q column and the only digit of the q-1 column are 0 and 1. Therefore, we have performed the a+1 operation. The calculation is written next to it. After we are done with the calculation, all the bits are shifted to the right and the binary number obtained after the last iteration is the required answer.
Now let's see one more example, minus 3 into minus 10. Here multiplier is minus 10 and we know binary number for 10 is 1010. We will add one extra sign bit, hence 01010. 2's complement of this number would be 10110 and this is the binary number for minus 10. As total number of bits in this number is 5, we will note down n is equals to 5. And also we would take 5-bit binary number for the multiplicand, that is m, which in this example is minus 3. Following the same procedure, binary number for 3 is 00011 and 2's complement of this number is 11101. Hence, our multiplicand is 11101. Now let's recall the rules. First, we initialize a and q minus 1 to 0 and we consider last digit of q, which we call q0, and q minus 1. If they are 0, 0 or 1, 1, we would do only right shift. If they are 0, 1, we will be doing a plus m and then right shift. If they are 1, 0, a minus m, then right shift, or in other words, add 2's complement of m to a and then right shift the whole thing. Also note down number of passes is equals to n. Hence there will be 5 passes in this example. In every pass we will check q0 and q minus 1 and every pass ends in a right shift. Like here, in first pass there is 0, 0 which is highlighted in green. Hence there will be only right shift. Similarly, in second pass there is 1, 0. Hence we will first do a minus m, that is we will add 00011 to a and then we will right shift the whole thing.
In step number 3, in a there is 4 times of 0 and 1. In q 10101 and q minus 1 there is 1. When in q their last digit is 1 and q minus 1 the last digit 1. When there is 1 1 we have to do only right shift. So we got 0000, 11010 and 1. When the last digit of q is 0 and q minus 1 is 1, we have to do a plus m and then right shift. So we got it 4 times of 1 and 0, and in q 11101 and in q minus 1 there is 0. In last step, step number 1, 4 times of 1 and 0, in q 3 times of 1 0 1 and in q minus 1 there is 0. So when there is 1 0 we have to do a minus m and then right shift. We can also say that a plus 2's complement of m and then add it and then we have to do right shift. So then we got it 5 times of 0 and 1110 and in q minus 1 there is 1. Therefore the final answer is 5 times of 0 and 4 times of 1 0, that is in decimal form means 30. So the final answer is of minus 3 into minus 10 is 30.
Here are 4 advantages of Booth's algorithm. First, reduce the number of partial products. Booth's algorithm reduces the number of partial products required to complete the multiplication process, which can save time and reduce the complexity of the computation. This is achieved through the encoding process, which replaces adjacent group of identical bits with a single partial product. Second, faster computation. Because Booth's algorithm require fewer partial product and fewer addition to arrive at the final product, it can be faster than other multiplication algorithms. This can be especially beneficial in computer hardware, where speed is crucial. Third, support signed integer. Booth's algorithm supports signed integers, which means it can be used for multiplication of both positive and negative numbers. This is not always the case with other multiplication algorithms, which may only support unsigned integers. Fourth, used in computer hardware. Booth's algorithm is often used in computer hardware such as in arithmetic logic unit. This is because it is a relatively simple algorithm that can be implemented in hardware with minimal complexity, which make it a cost-effective option for hardware design. Overall, Booth's algorithm is a useful and efficient algorithm for binary multiplication that can be used in a variety of applications. Its advantages included reduced number of partial products, faster computation, supports for signed integer, and applicability to computer hardware. Next, here are 4 disadvantages of Booth's algorithm. First, need for extra hardware for encoding. Booth's algorithm require extra hardware for encoding, which can increase the cost and complexity for the hardware design. This hardware is needed to determine the appropriate partial product to be added or subtracted at each step of the multiplication process. Second, possibility of overflow or underflow error. Booth's algorithms is prone to overflow or underflow error if the result of the multiplication is too large or too small to the represented by the available number of bits. This can be a problem in certain applications, especially if the multiplication result is used as input for further calculation. Third, not optimal for small multipliers. Booth's algorithm is not optimal for small multipliers, as the encoding process can be actually increase the number of partial products required to complete the multiplication. For small multipliers, the standard multiplication algorithm may be a more efficient option. Fourth, complexity for non-power of 2 multipliers. Booth's algorithm is more complex for non-power of 2 multipliers, as the encoding process may be require additional step to determine the appropriate partial products to be added or subtracted. This can increase the computational complexity of the algorithm and make it less efficient for this type of multiplication. Overall, while Booth's algorithm has several advantages, it also has some limitations and drawbacks that should be considered when decided whether to use it for binary multiplication. The need for extra hardware for encoding, possibility of overflow or underflow error, complexity for non-power of 2 multipliers, and efficiency of small multipliers are all factors to consider.